looking at G-GMD.A.1, activity number 3. This activity focuses on the area of a triangle. And the area of a triangle is, you're going to see, we're going to look at it in a couple of different ways. And they're all based off this idea of, again, the formula of base times height of a rectangle. Actually, all of the formulas stem from that very basic idea of an array, of a base and a height, and so on. So the first one is kind of the classic idea of thinking of a triangle inside of the rectangle that encloses it. And so what we're talking about there is if we were to create a rectangle here that enclosed the same base and the same height, how is it that the formula for a triangle is 1/2 the base times the height? And you'll see this very clearly here, that it creates two sets of congruent triangles, one here and one here, one here and one here. And so if there are two sets of these triangles and they're congruent, and your triangle only has one of the two sets, you are 1/2 of that area. So the original area of the rectangle is base times height, but because our triangle is enclosed in that and exactly half of it, we get a new formula, 1/2 base times height. That one could take on some different looks, but it's all the same idea of enclosing it inside. Another is one of dissection, and there are many ways to dissect a triangle to make the formula make sense. Let me just look at a couple here. One way might be to split it in half. So if we took the original height and we did half of that height, what happens is it creates, again, a nice little rectangle here. And this rectangle, how do we fill it? Well, this little piece here would fit right here, and this little piece fits in here. They fit there because of this idea of the same slope. They fit there because of the same cuts and dissection. And what eventually happens is we fill in this new rectangular region. And this new rectangle, its dimensions are the same base, but exactly half the height. There it is again, half the height times the base. Another way might be to split the base in half. And so we might go this way and rotate this piece up into here. And we would obtain, again, a new rectangle. This rectangle would have half of its base, but its full height, which, again, is the same formula. Dissection is fun, to cut it up, move it around, and see how there are many ways you can do that. Shearing, which is kind of a new technique, I think, to most of you. And again, if you watch the last one, you'll see the idea of shearing there. And we'll do it again here. Is this idea of locking in one dimension. So we would lock in this base. And then moving along a parallel plane, a parallel line, we would move that vertex until we obtained whatever we wanted. Normally, we would maybe move it until we got a perpendicular here, and then it's very easy to see this new calculation of base times height, 1/2 of base times height. Sometimes you shear it on a grid so that you can calculate its base easily, so it's a horizontal or a vertical base, and then it's easy to count base and height from there. When you have an obtuse angle, many students don't like how the height is outside of the triangle. And so by shearing it, again, moving it along a parallel line, moving this parallel to this, we might adjust it until we get to this location, which would have the exact same area, but might be a little bit easier for you to calculate. Finally, something I call the box technique, finding the area of a triangle on a grid. The best way, especially when it's a weird one like this, different slopes, nobody's horizontal or vertical, is enclose it in a box. So in other words, create some sort of rectangular region around that shape. And then notice it makes one, a big rectangle, and then what you do is you subtract out the little guys. This guy, subtract out this guy, subtract out this guy. And when you subtract those pieces out, what's left is the area of that quite unique or awkward looking triangle. We'll look at a couple up close to give you an idea. Let's next use the idea of the triangle being half of the area of a rectangle. So first, if you put a rectangle to encompass the same base and height, you would get a rectangle that looks like this. You start to see this two congruent set idea, that this triangle has a partner here, and so that's half of that region, and this group has a partner here that it is half of as well. So when we look at it here, we see kind of this is half of this and this is half of this. So overall, it's exactly half of the area of a rectangle with the same base and height. So another reason we get 1/2 base times height. Let's look at the idea of doing a little dissecting in a half here. The idea would be to cut your triangle's height, let's say in this case, in half, and then to do a little bit of moving. So we have this upper area that we want to move around. We would bring down, say, this little piece into this spot so that that guy goes there. And then we'd bring this guy into this position. It's hard to see, but there's a rectangle that's formed there. Let me show it to you here. So when those are placed there, what we have is all of the area regions filled into a rectangle. And you'll know it's the same base and it's half of the original height. And so there is 1/2 the height times the base. There's a nice way to make sense of that formula. Shearing has the same principle in triangles. If we lock down our base but shear our other vertex in a parallel manner, you'll notice that the base stays the same as 6 and the height stays the same as 3. So base times height divided by 2 still remains to be the exact same size. So this is the shearing process, and it doesn't matter whether if I change this and I change my height. Again, notice that it shears to be all of the same. Quite a neat little principle that's often not used at all in finding area. Let's look at a tricky shearing case. I might use the box technique here instead. Actually, I probably would almost every time, but let me show you a shearing case. So the key is to notice none of these are horizontal or vertical. So let's get one that way. And what I'm going to do is I'm going to create a parallel line that I can shear along. Now, when I stay parallel to, I'm going to call this my base. When I move this point along there, I can go anywhere along here to obtain my value, my height. And so I might be interested in this spot here. And the reason I might be interested in that is that this triangle, this triangle here is exactly the same area as the original. Let me outline this area here. So you can see that now things are getting a little bit easier because I'm on the grid here for 4, or not quite 4, I guess. And then I have a height here. Let me give you an example where shearing can be a little bit tricky, but also quite useful. Here's quite an awkward looking triangle in terms of finding its area. And the key idea is to lock down one base like this, and then to create a parallel line to that base. And then all you want to do is find a point somewhere along that line that will create, say, a vertical line. Here's a case where that would happen. So here, this triangle, in kind of a very cool way, is exactly the same area as that original guy. And the reason is this base stayed the same, and then the height is being sheared along here. Now this is much easier to calculate in this format because there's the base of 2, and perpendicular to that would be a height of 2. So 2 times 2 is 4, divided by 2 is 2. So that very awkward original guy, this guy here, while that is a very tricky region to calculate, this is not. So by doing that nice little shearing to make one of the sides vertical or horizontal, it becomes easy on a grid to count a base and a height and calculate the area. Very cool. Straight the box technique instead of shearing here. The box technique is very cool, and actually is just to create the rectangle or a square in some cases around the original shape. What that does is it creates some triangles that exist around the edge of that triangle. Here they all are. And what happens there is that to find this area, you just take the large rectangular shape, which in this case is 1, 2, 3, 4 times 1, 2, 3, 4, 16. So you know the total area is 16. And then you can calculate the area of this right triangle, this right triangle, and this right triangle. And right triangles are very easy to calculate area compared to this guy, and then subtract them, and what's left over is the inner region. That's the concept of the box technique, a very quick and simple technique.